Welcome, everyone. Welcome, and thank you for joining us this afternoon for a lecture on causal AI. I'm thrilled you could join us. My name is Rodman Reif. I'm from the class of 1969. You can call me Rod. I majored in electrical engineering and computer science and spent more than 30 years in the banking and brokerage industries, using computers and other technologies to modernize payment systems around the world. AI has been part of the modernization effort. You've seen it in both credit card authorizations, using neural networks, and in fighting fraud with today's AI technologies. And in fact, this week, Visa announced that they're putting an AI system in the UK to fight fraud. Elias Berenbaum is an associate professor in the Department of Computer Science and is the director of the Causal Artificial Intelligence Causal AI Laboratory at Columbia. His research focuses on causal and counterfactual inference and their applications to data-driven fields in health and social sciences, as well as artificial intelligence and machine learning. His work was the first to propose a general solution to the problem of data fusion, providing practical methods for combining data sets generated under different experimental conditions and plagued with biases. More recently, Professor Berenbaum has been exploring the interaction of causal inference with decision-making, including reinforcement learning and explainability, including fairness analysis. Before joining Columbia, he was an assistant professor at Purdue University and received a PhD in computer science from the University of California in Los Angeles. Professor Berenbaum was named one of AI's 10 to watch by the IEEE and is a recipient of an NSF Career Award, the Dan David Prize Scholarship, the 2014 AAAI Outstanding Paper Award, and the 2019 UAI Best Paper Award. Please join me in welcoming Professor Berenbaum.
Thank you, Rod. Good afternoon. Pleasure to be here. Welcome to Columbia. My name is Elias, Professor Elias Berenbaum. I'm, as I said, director of the Causal AI Lab. If you're on Twitter, follow me there. There is some kind of news related to AI and causality usually there, this interesting discussions. Today I'll be talking about...
Use the mic, please.
The mic?
Yeah.
Let me try to be... Can you hear me now? Okay. Okay. I usually like to be up front. What's that? Oh, okay. A little bit higher volume here. Okay. Yes. Is it good? Yeah. Hard to me to keep here and don't move, but I'll try. It's I usually around and moving and. Right. I usually like to be upfront about the goal here, or the main hypothesis of the conversation or the lecture. I think the main point is that, first of all, there's a lot of cool stuff happening in AI nowadays, and I think everyone is excited, me included. Now, the main point that I'll try to make throughout the talk is about still there is some kind of fundamental barriers towards more general types of AI. We are just in the very beginning, kind of the little tip of the iceberg, and in the questions about what are these fundamental barriers, I'll try to describe some of these barriers and the challenges, and then I'll try to share my hypothesis about what connects them and what is kind of missing, or how to circumvent them, how to tackle this problem. But not a mystery book here. I think the main one is like most of the AI today, including kind of credit fraud analysis, as Rod said. Thanks for the introduction, Rod. It's very correlational. It's very based on statistics or in the correlations that are in the data. And as we can see or can understand as humans, but we also have evidence from the cognitive sciences, from psychology, and so on. Humans are kind of causal machines. Usually we have a model of the world in our brains, a causal model. We have our goals, our expectations, and so on. And then we start kind of establishing plans how to move the current reality towards however we would like the world to look like. And this is based on a sequence of causal actions or actions, and which is very hard to do with the current, just purely based on correlation. Then let me try to elaborate on that. I do assume that there is some level of knowledge about what is AI, but you share, you can kind of scream there or share with me if there is something that is not clear. It will be more like a general talk. But, and I'll start with some references. If you want to learn more about it, in addition to my website, Causal AI, or my lab's website, I should say, causalai.net. This is a paper from with Professor Yuda Pro. That was my advisor. His Turing Award, considered Nobel Prize in Computer Science, that appeared a few years back in the proceedings of the National Academy, saying causal inference and the data fusion problem. That is exactly about how should we be synthesizing data that usually is word of the bio that I didn't realize. The word bias is kind of technical word. Humans use bias in the general discourse in a different way. What I mean by bias, or what people in the field mean by bias, is like confounding bias, sampling selection bias, generalizability bias, internal, external validity. If you heard this word, this is more technical bias that you are referring there. Otherwise, you can ignore what I just said. It's fine. But there is some kind of hints there in this, some type of discussion in this paper, the causal inference and the data fusion problem. This is almost like a summary of the field. This is another paper that we have that's a basic one, basic in the sense of fundamental, called Pearl's hierarchy and the foundations of causal inference. It's some type of introduction to the field of causality. I'll share other reference later, the introductory. And this is another paper trying to relate causality with, or explain what is the connection between causality and neural nets and deep learning. Part of the renewed interest in AI and a lot of the hype is related to some breakthrough that happened maybe depends on how you count history, but between 5 and 10 years ago, related to how handle larger amounts of data through neural nets. That is a tech that we knew for, I don't know, at least 50 years plus. Maybe when some of you are here, we are kind of discovering, or we already kind of had neural nets as a kid in the block, in the zoo. There is a very new interest in the last 5 to 10 years given to some type of breakthroughs, including by Yoshua Bengio, that is a co-author in this paper. Still, the original one is pretty much correlational. This is the first paper that I'm aware that we're from 2021 that is trying to explain what is the relationship between these things. Should be, I'll elaborate on that, but at least we'll have the reference. Then, as I was saying, we have recent breakthroughs in AI, machine learning, and DS, data science. I have our Data Science Institute here, one piece of that. Systems are able to perform extremely well in making predictions in high-dimensional settings. In particular, there is huge amount of progress in fields from natural language processing, how to do processing of human speech. Computer vision, if you heard, right, we take a picture of the scene, there's a camera there, and you start being able to do image segmentation, detect that this is a human, this is a bottle, this is a computer, and so on. It took maybe 40, 50 years until we could do it. Now we are kind of doing it relatively well. It's a standard class nowadays, and we kind of teach this type of things in basic ML, and also in reinforcement learning. I assume there is some level of understanding of RL, even though it's less common, but the summary here, RL is the machine learning version for decision-making under uncertainty. When you don't fully understand how the environment works, I don't have the laws of nature for many of the environments or the equations for many of the environments related to human interactions. There is this sub-area of AI, it's a huge one called RL, or reinforcement learning, that is concerned about that. Then we also have classes on this type. But these three, we have for the three of them: natural language, NLP, natural language processing, computer vision, and reinforcement learning. And most of the progress is around there. You can pick at random now, just Google and get some kind of exciting things that are going on in this field using some of the stack. AI and robotics are helping to optimize farms to increase the productivity of crop of yields or yield crops. This is related to the AI and wearable cameras in self-walking robotic exoskeletons, and you can also help people with some types of disabilities and how to calibrate and so on. This is related to the AI that is better than human doctors, supposedly better than the human doctors at predicting breast cancer. Now, when you do some kind of breast cancer exam, and you used to send to people that will check the image and see what's happening there. Now, one of the people, as I understand, we're already not sending to, you need more than one, but now one of them is already a AI type of system. AI systems is better than, yeah, okay. Now the question here, this is kind of great, and you can go all over the place now. This is maybe, anyhow, it's all over the place, and there are a wave of companies building on the text coming from natural language, computer vision, and reinforcement learning. Now the natural question here for the scientist or someone that is more mathematically inclined, will be, does this mean that we are, if we're kind of analyzing the theory of what we have done so far in the last, I don't know, 5 decades, the natural question is like, does this mean that we are done? We just need to train more students and oh, something is happening, train more students, I don't know, hire more people, make more buildings and put the AI engineers there and put more energy, right? A few $1 billion later, maybe the world will be completely different. And I think this is already happening. I'm just describing something that's happened. The question is like, is this enough, right? And important here, that is not a detail, but I will put as a detail here, a footnote. But this is under the assumption that we have infinite amount of computation and data. And I will elaborate, but everything that we do so far, that we are successful, does rely on crazy amounts of compute, as we say here in the jargon, and also data. And the question is about what if the answer is no, what may be missing in the more foundational side, in addition to having infinite amount of compute. Let's assume this idealistic kind of dream scenario, an infinite amount of data and budget to hire people. Essentially, yes.
Doesn't this set of assumptions also include that the data is highly accurate? Like that the error rate is minimal? Because if the error rate is very high...
Yes. Accurate, and not only that, I'm putting a lot under the rug here, but accurate and also very heterogeneous. In other words, it's covering everything that is possibly happening in the world, which is totally unrealistic for any reasonable setting, because things will blow up in terms of number of possibilities, right? In an exponential way, then we cannot cover all the possibilities. I don't know, if you have 10 binary variables, you already have 1,024. You have, I don't know, 20, you have 1 million possibilities, right, or configurations. If you need to learn to samples that will cover the support or distribution like that, it's totally impossible already. And it's, of course, you cannot have this full diversity in some sense. It's not realistic. And I will elaborate more on the diversity, the heterogeneity of the data that we need as well. Now, this is something missing, and then this is some of the current challenges in AI and ML. This is just from the news. Gary Marcus, professor of cognitive science and psychology here at NYU, big critic of the current generation of AI, talk about the COVID. This was around the COVID-19, and say that this should be a wake-up call for AI. Meaning, you can say crazy things about what is going on in AI. I would say it's not unfair to say that it was a miserably fail. We miserably failed in the COVID. We helped essentially, we can do corner cases here, but essentially zero. The world was in complete chaos, right? It was quite bad. And I don't think that we contributed in any meaningful way. Then you can talk about the moon, but we cannot solve even the most mundane problem that knocked in our doors. Some kind of teaching, some level of humility for the kind of claims or be sober in the claims that we're trying to make. This is about making the role of AI in breast cancer explainable. There's a very cool stuff that you can kind of outsource some of the detection and the diagnosis for breast cancer, but this is kind of, if you zoom in, things can be quite bad as well, given that we have many of our systems are black box. The level of understanding of these systems are very low in reality. This is about Nature paper related to the fair way forward for AI in healthcare. Then again, it's a huge industry. Healthcare itself and the health science in general is, I think, 1/6 of the general economy. And AI, people are very excited about AI. Question is about even using the data, and if you have huge amounts and are accurate, one observation, it's very basic, but in some way people don't realize, AI is trained with data, even if you have accurate data. But data is nothing more than a picture of what's currently going on in the world. Because what do you think that is data? It's just a picture of the world, right? But if the world is messed up in some way, and it is no great news here, but there are many problems in the current version of the world, then what do we expect that the AI will be doing? It doesn't need to have a PhD here in AI or in CS or double E. It's like, of course, AI is essentially just in a tabula rasa, in a kind of almost like a chip shot way, is trying to to learn the patterns that are in the data. The data is the picture of reality. AI is just trying to recover these patterns. Many times, of course, there is this dressing of being something super modern and amazing in some way, but still, it is a black box, and then we start replicating what were the patterns that were caught from reality, and sometimes even amplifying them. We can prove that, by the way. I'll talk with a lot of words here, but everything that I'm saying, you can find a theorem, we can show it formally. Then it's, I would say, quite dramatic, the picture here. And I'm not negative. I'm just trying to diagnose, to be real about what's happening in order to move forward. Yes?
So you say the systems are a black box. Is that, which means that we don't know how the system came up with the conclusions that it did, right? Is that intrinsic to the design, or is that just because systems haven't been built that put markers on what their process is?
Intrinsic, at the moment, totally intrinsic in the design, and it's non-trivial, meaning after the realization, the comment that I made, people don't like that, of course. Now the question...
Even after it's developed, you can't go back and sort of reverse...
That's what I'm saying. There is something that is quite brittle about the tech that we are using, and there are attempts all over the place. There are, I don't know, now 5+ years of literature, maybe 10, of people trying to patch things around in order to try to expose why the system is doing things in the way that it is doing, and is usually we are failing miserably. And the message, like, there is something fundamentally wrong, or that doesn't doesn't lead to this type of properties that we would like to, that is related to have some level of transparency and explanation. Exactly the point. Very scary. It is scary. I'll be positive in general, but we should notice that we are not in the best position at the moment. We should be aware. And I should say, by the way, to be clear, I don't have all the answers. There's no magic here. I do have some answers, and I have gut feeling, and we have good theory, and so on, and some kind of roadmap, but we don't have, this is a kind of generational effort in reality. There's no silver bullet. But as I said before about the upfront, I am advocating for a different approach from the current mainstream about what we're doing. That's true. No, that's it. Transparently, given that I'm a professor of cause and effect, causality, the transparency is the effect. The question is about what could lead to this type of property that we like from the systems. And the answer would be, we would like the systems to be somewhat more causal. Now we would like to define what is causal and how to build systems that are like that. Yes?
In healthcare analysis, there's no doubt that AI is going to improve and expand, but are they also working on the outliers who have a set of data, and 99% of the patients may have a proven problem, but 1% has something else?
Yeah, it is. I would say the answer, yes, this is a consideration. We even the non-causal part of the analysis. There is, from the 80s to the 90s, before the 80s, AI exists with this official name, it goes back for centuries in my view, but officially from the 50s, 1950s. Now, the modern version of history. Now, until the 80s, approximately, it was pretty much based on logic, on mathematical logic. It was kind of very Boolean and somewhat critical, very aligned with the tradition for kind of pure mathematics or mathematical logic, as it's called. Now, from the 80s, mid-80s and 90s, this started kind of booming, because the deep learning at the time was about, man, it's not a good idea to use logic. It's too brittle, because there is nothing that is 100% or 0%. Then they start trying to inject, there's a kind of principal way of doing that, probability theory, decision theory, probability theory in AI. And then kind of change the field. But even this approach that was a step in the right direction, but doesn't solve the problems that I'm saying here, it's already kind of aware and trying to handle some of the outliers and have a more probability software, instead of being hard, a software version of making a statement. Right? It's protected by probabilities and some kind of bounds and so on. But I would say that it is a concern, but the whole is much different than this one, than the handling the outliers. And so on. Even the 99% who don't know how to handle the well, in some sense. I would like to make it specific in which sense this means. Yes?
Is what's called fuzzy logic an instance of what you just said about probabilistic AI?
Yeah, it depends on how you want. This is a taxonomy now, right? It depends on who are the winners or the losers in the historical context in the war in some way. And they usually do the branding. I would say it's not far-fetched, but it was Zade, I think was the name of a professor in Berkeley that kind of pushed that. And I would say I wouldn't say that was the winner in some ways. A very small community nowadays, after maybe 3 or 4 decades since it started. But yeah, it is in the bucket of kind of software. Of course, a different take in probability theory. Happy to talk offline, but if you want to be inclusive, yes, it is a probability-like approach, probabilistic-like approach. Here's a piece of news saying why AI, with examples about why AI struggles to grasp causal effect. This is another from the MIT Tech Review. I know Brian Bergstein. The AI will not be very smart if computers don't grasp cause and effect. That's something even humans have. This is an interesting, wouldn't be I understand that this piece. Recommended piece, by the way, I share some opinions there, but that's something even humans have trouble with, which is true in some way, even though I think mostly we do okay, and we survive, and we do well in life, and we are here for a good amount of time, then I do feel that we have a grasp of causality in some way, at least many humans. It's true that the world can be insane in some other ways, but I would say there is always a percentage of the humans that are connected to causality and something kind of more systematic. And then there are still serious foundational issues in AI. And I would say, kind of summary, current AI systems suffer from lack of understanding or explainability capabilities. And what I mean is like, what the AI, even AIs that are doing quite cool stuff, it's kind of very, the irony that they made the name deep learning, but it's quite shallow in reality, the type of understanding that the systems have, compared at least to humans. They are kind of prone to unfair and unethical decision making in the sense of that I just described before, because they are totally agnostic to anything. They're just replicating the patterns in a way. In the optimistic side here, if you want to put the optimistic hat, given that they are totally kind of oblivious, they're just replicating the patterns and they don't have any will or autonomy. This means that if you do it right, we can kind of try to bias the system to correct things that are hard to do with humans. There are cases, for example, it's kind of interesting that they are analyzing sentences related to judges and trying to understand if they are allowed, If they are more lenient or less lenient in their decisions. They are giving allowing for the bail or not allowing. And then you check the time that the decision came out, and depending if it's before or after lunch, maybe the decisions would change very significantly. Which is like, it's kind of the level of robustness. It sounds like a joke, but it is not. It is true. Then and all the cases related to anyhow, I have, regardless of my opinions, but it is true that there are serious issues of bias of how humans, whatever, if the person, depending on the country too, but if you're a friend of the person, maybe they will be leaning to maybe give you a raise. If you don't like the person for whatever reason, they will be less. And there's all kinds of bias like that even if you go to the manager or whoever is doing the thing and say, let's do some training, or this is not the right way to do, and so on, it is highly non-trivial to humans to change. It's possible, but it's non-trivial on average to humans to change. While for AI, it doesn't matter, right? AI is not committed. It's replicating the patterns, but it's not committed in any sense. Then this is the optimistic side here, that this could be a solution for correct some of our biases if you have a way of encoding it properly that wouldn't be possible in the real world. Then we are kind of moving the world towards our ideal version instead of replicating or amplifying even the biases. Yes?
Professor, where we have here unfair and ethical decision-making with current AI technology, would that be because the training data was in some way unfair or unethical?
Exactly. As I mentioned, yes. Because data is nothing more, as I said, of the picture of reality. And if reality has their problems, the AI will just be capturing these patterns and replicating it, and sometimes even amplifying it. They are very kind of data hunger and sample inefficient. There are some sample inefficiency. Sometimes a human or even a kid, a baby, is able to do stuff with very few examples. Right? We teach once, twice, 3 times, and the person is able to get it. While any of these systems, most of the times we need 3 million examples or 20 million examples in order for AI to start doing what you expect, which is kind of insane in some way, but in other way it's kind of very revealing, because it just say that there is something fundamentally different between how these entities, us and Homo sapiens, and the AI is operating now. And there is no right and wrong. Of course, there is good stuff happening in the digital computers, but still, for learning, it doesn't seem to be a great idea. We're talking about learning, right, in some sense, and decision making here. They're very non-robust. It's poorly robust and generalizable. If you train maybe AI to operate and clean this room, you have the machine that is cleaning the room, or operating and serving beverages or something. Great. Maybe working after, I say, data hunger, you spend 10,000 hours, taught the AI is doing that well in this environment. Now you move to the other auditorium in the other building, the AI will be very clunky and wouldn't be able to adapt. Which for humans, maybe is the first time that we're in this place, and still we're already being in other places that are similar to that, and we are able to capture, in an implicit way many times, the invariances that are in the environment. In other words, we have quote-unquote real understanding, and whereas it doesn't matter if I never saw the chair in this way or the beverage was with this color, I can see the fridge there, there is some kind of bottle that I understand the concept, the chair, there's so many details that I don't care, but it's still a chair. Then we are able to generalize and move without thinking. I understand that may be unusual, you're not used to think like that because you're automatically doing that. And AI really struggles to do this type of things. Given the title of the talk and the current hype, I would say a connection here is like there are missing, current AI has missing causal generative capabilities. And I will elaborate on that and all of them, or many of them. But I would say for now that in our brains, we are doing some type of simulation there and predicting stuff. It's not that I will always act in the world. If I want to test how this works, I will just move here the bottle to understand maybe gravity, that something will drop. And no, I'm kind of running in my brain some type of simulation and predicting what would have happened had I start moving this bottle. Maybe you'll make a big mess. People will be unhappy with me. They give me more work later. I'm doing this speculation or this simulation in reality in the brain. Then this is very related to simulation. another name for generative capabilities. We can generate this counterfactual, these different scenarios that didn't happen in the world, and see if they are desirable or not desirable. Then this is an important building block of our cognitive system.
I'm not sure I understand the inability to generate causal hypotheses?
Right, causally consistent scenarios, yes, yeah. And I'll show toy-ish examples soon, but yes. Those are kind of very thorny. They're not new problems. I'm just organizing them here, cataloging them here. The thorny, decades-old problems or tasks. I should say later I'll do more advertisement. I'm finishing a book, and the book, each part of the book is one of these bullets, because I think we have good mathematics and theory to solve them, and applications and the translation. But those are hard problems. And the question here is about what do they have in common? Because it seems very disparate. I'm talking about everything that is in the world in some way. And EB here, Elias is speaking. I would say all of them need some type of understanding of the causality, or they kind of miss the causal inference component that is underneath these problems that you can kind of model. Then I would say, broadly speaking, what is missing in the AI? I would say we need kind of more causal inference capabilities. To have a world model that is a causal model, that is not, of course, is not the data. The data is a superficial, again, picture of the current reality. We understand the world in a much different way than the pure data. Now we have a model. We start having our goals, expectations, beliefs, dreams, and then we can start operating with other agents that have a model like that too. In any case, let me ground this point and try to move towards the Gen AI. One recommendation that this book was written by Pearl, Yuda Pearl and Dana McKenzie. But it's a summary of Pearl's work, maybe in view, and how causal is a book, not non-technical book. I read the book and like the book, but you will not find a lot of mathematics. I usually describe my mom, and so she's not a scientist. But I think everyone can understand it's a very beautiful kind of history of causality going back to thousands of years, and how this is important for humans, independent of your view, but even how to differentiate that from other species, and the idea of having the imagination and thinking, building this world model and entertaining different versions of the world. Then recommending. But why I'm saying that? Because one important result that start allowing us to ground and move towards the causal AI is that each causal model, and I will use it in words here, but again, you can make it precise. Causal model is nothing more than, if you think about physics, is a collection of mechanisms. And the same exists for human relationships, or anything that is happening at the macro level, not only at the quantum or small level. But each causal model generates what we're calling this Pearl causal hierarchy, or the PCH. If you took a class in algorithms here when we are here, or automata theory, or things like that, you have this thing called the Chomsky hierarchy. I don't know if you remember, but you have these regular languages, context-sensitive languages, Turing machines, and so on. Now, it's some type of hierarchy of the strength of the different languages to describe computation. Here, this called Pearl causal hierarchy, PCH. The PCH is not a computational hierarchy as the Chomsky hierarchy, but is a hierarchy in terms of understanding. There are different levels of the hierarchy, and the book describes that in general words. I will use some type of summary here and a little bit of formalism. The first layer of the hierarchy is related to associations or correlations. I put I there because it's related to our activity, humans' activities of seeing. We're just put our hands in the back, and we're just, through our perception, through our eyes, maybe ears too, we are kind of observing the world unfolding, and we are collecting this data, tons of data. Now, the typical question that we may be asked that is related to this modality of interaction with the world is, how would seeing, let's say, a variable x, a random variable x, change my belief in a statement y? Concretely, somewhat concretely, what does a symptom tell us about the disease? The symptom is the x and the disease is the y. And then we do some computation there, trying to learn about the disease when you have the system, the symptom. Symbolically, symbolically, if you want to start formalizing that, you can write something like that as the probability, or ask about probability theory. What is the probability given that you observe the big variable x is equal to little x? What is the probability of the event y? Observe that the person was sick in some way. What are the causes of this, for example? What may be causing this symptom? The purely association so far, again, from I was alluding to in one of the conversations here, around 1980, this symbol and this notation exists maybe for 300 plus years, but in AI, it's kind of officially started in 1985, 1986, that when people start kind of more clearly realizing that maybe you shouldn't be Boolean, you should put a probability in this proposition y is equal to little y. In machine learning, if you heard, it's very related to the tasks that we call supervised learning. Supervised or unsupervised learning. Usually you say, maybe I see this collection of pictures, and I will ask, oh, is this a cat or a dog? The probabilistic interpretation of what we do in supervised learning. Now, depending on the decade, we have a different theory or a different algorithm that will try to evaluate expressions like that. For example, in the 80s and 90s, maybe you have and even around that, we have Bayes nets, or decision tree, or support vector machine, or deep neural net. Each time we have some kind of new trick that would allow us to evaluate something like that. Why is it hard? By the way, we could ask what these guys are doing, why they're spending decades doing this type of things. The hardness here comes for scale. It's very hard to scale these things. Usually, anyhow, 300 years we could do with binary variables in games of chance. And what's the probability of the move of the opponent there? When you have a little game, when you're starting inventing the games, board games, and so on. Poker. Now, poker is already refined, much basic versions of that. Nowadays, you can take this X with millions of variables. And even though it looks the same in this slide, you can give a course just how to evaluate this expression. And it's non-trivial. But okay, but this is good. This is layer one of the hierarchy. Now what about, are we done? Not really, because we are not just seeing, we are not just getting our hands and putting the back and just lay down there and seeing the world to unfold. Usually we interact in the world, we do something. Then this is related to layer two, that's called the interventional layer. It's related to the activity of doing. What if I do X? What if I take the aspirin? Will my headache be cured? What's the effect of my action? Symbolically, we can write this, I put a muscle here. Symbolically, because we guys with their own volition, their own free will, they are deciding, they are intervening in the world. 1 second. Symbolically, we need to introduce a new operator that is different than the conditioning. Now I have the do operator. What's the probability of the event y? Maybe the person will be alive. Had we given the drug X to the person, and you observe a context C. And the context would be, again, a 1 billion variable. This is the age, this is the gender, this is the DNA, this is the socioeconomic stuff, whatever is the 1 million vector type of try to capture some of the invariance, or some sort of the peculiarity, I should say, of the features of the unit that we are considering. But anyhow, this was around 2000 that we are between 90s and 2000 that this notation was introduced. And when I talk about bias, there's a clear difference between these ones. When I say correlation is not causation, formally, this is the difference between this distribution, this probability distribution, and this probability. Now, there is different formalism also in machine learning that allows us to handle something related to that. The modality that I mentioned earlier, that's called reinforcement learning, is the counterpart. And there's also the languages of the formalism that ground that. For example, if you heard about, also from the 60s, I think, from Bellman, the Markov decision processes, MDPs, right? And then you have the PO MDPs, the partial observable Markov decision process. And then you have others after that, but still, those are kind of the formalisms that kind of ground this task We're going to say something.
Sorry, the question was about sequence.
Oh, okay.
I was just asking about what the variable was, the context.
Okay. This is layer 2. Now what about, are we done? No, because humans are not just perceptual machines that are getting input in, photons or some kind of stimuli, and then just act. We're just not doing only that. We're not autonomous. We're complicated automata, but it's not, I think we're not only that. Hard to show, by the way, but I'll defer for the chat. The third layer is related to the counterfactual. Factual is meaning what's happening in the world, and counter is like contrary to what happened in the world. This layer is very, I put a brain here, is very related to the imagination. Seems to be a distinct feature. In the Book of Why, there's a good amount of discussion, there are many pages, and it seems to be a feature that is very peculiar for humans. We are sometimes able to put things together that it is totally not in the world. You can go back to some caves and see people putting the face of the human with the body of an animal. There is no, in the factual world, we cannot see that. But still, as an expression of art, right, or some kind of, for some inspiration, some artists a few thousand years ago decided to draw that in a cave. How is this possible? We don't see other animals putting things together in this way. And it seems a distinct feature of the humans. Of course, this is a baby version, it's a very rudimentary. We do that all the time with much other of our endeavors, right? If you want to make the world a better place, we need to be able to entertain what is this thing, right? In order to move reality towards this direction. And we need to be able to formalize what is outside the data. Now, this is layer 3, or counterfactual layer, very related also to retrospection or introspection. This is what gives I don't know if I mentioned, but the book that I mentioned by Proust called the Book of Why. It turns out that you can formalize another very important feature of humans, that is ask why. We can formalize the why question in this notation of the counterfactual. I'm not doing that here. I teach a whole year's 2 classes, a sequence, to try to ground this slide. But anyhow, that's the notation. Why something happened the way that they happen, and the mathematics for that. Or what if I had acted differently? Maybe I ate the cookie earlier in the breakfast. Maybe I shouldn't if I try to do a diet. Then what would happen? Maybe it would be, 100 grams lower weight. We can speculate that. Maybe because we have a very clean model, at least for this particular situation. We can entertain this idea. We are allowed to do that. I'll get that 1 second. Was it the aspirin that stopped my headache? Just one example here in the symbol, because it gets more convoluted, and I will avoid too much of that. But maybe the guy took the drug. Joe took the drug, that is the X prime. Big X is equal to X prime. And Joe is dead. He's gone, unfortunately. That is the Y prime. This is happening in the factual world. You can go to the data. But now we are allowed to ask, why? Or would Joe be alive, that is Y, that is the opposite of Y prime, had he not taken the drug, that is X, that is the opposite of X prime? Some very related to the idea of responsibility, right? Credit assignment, blame, responsibility. If you say that, yes, probability that Joe would be alive had he not taken the drug, given that he took and he's dead, is high, it means that the drug is to blame. Maybe you can sue the company, or you can just understand about the system, right? Of course, I'm just grounding some example, but X, Y's, and Z's and C's can be anything in the world. We have a language to express this idea. We have a primitive to talk about these counterfactual worlds. Yes.
So with all these levels, is the goal to actually admit point probability or probability distribution? Yeah, the whole distribution.
Yes.
Is it also recalibrated?
But here, one step before even thinking about notion of calibration, that is about, are these even well defined? even though we talk about reinforcement learning, it's a very specific version of layer 2. To be elaborated, but it's a fraction, a fragment of layer 2. Layer 2 is essentially inexistent in the current AI. Then the discussion here, the conversation is about, how do you define that? Because humans are using that all the time. It is very important primitive for us. It gives us some value. If you want to have the AI system that is more understandable or explainable or so on, in some way you should align with our primitives about how you parse the world, how are human lenses for the world. Then absent at the moment shouldn't be, of course. Now calibration, statistical efficiency, of course, maybe yes, if you want to. Yeah, not there. Now, what's the challenge? It is because beautiful picture, a cartoon, there is the cute guys there, the astronaut, and so on. Now, why is this hard? Because if it's true what you're saying, that it is well defined, right, in some way, and we can spend a few hours in just defining, writing down the setup and showing that things work, then why anything that we're saying is very hard? And the reason is the following. Most of the inferences that we are kind of care about or would like to do is not only from one layer. In reality, the inference are across layers. Meaning, suppose that you get input that you get tons of data that is coming from observations, that you are literally seeing the world unfold, or you're reading a book, or you're talking to someone, but it's observational, whether the name for layer 1 is observation, that comes from seeing, from observing. Now, 99% of the data in the world today is of layer 1 type. Very hard. It's a fraction of the fraction that is layer 2 type. If you're considering, for example, area that is more applied, I'm talking in general here, but I mean this in the medical domain too. Now, in the medical domain, there's a fraction of the data that the FDA requires drug approval. We spend maybe 100, 200 billion per year running these trials. It's very useful and so on. They are coming from layer 2. They are about the effect of actions. There is a randomization device, a placebo, and the drug, you randomize and you give the drug to some people and the placebo to the other people. And you are able to learn, quote unquote, what is the effect of the drug. It's not only confounding, it's not only spurious, it's the true causal effect. Assuming that the trial works well. Not the talk here today, happy to give some data or talk with you about that. We're assuming the perfect scenario for the trial that sometimes happens, you get data from layer 2. This is a tiny fraction of the data in the world. Because it's very hard. Each trial costs a few $1 million. Then it's very hard to do experimentation. First, it's expensive, but even if you have all the money in the world, you have ethical constraints as well. We cannot do experimentation with human subjects. They're not mice, right? They're not guinea pigs here. Then it's non-trivial. It's non-trivial even for layer 2 to get data from there. It's very valuable. It's a more detailed version of the world than layer 1, but still, most of the data that you have in the world is observational, passive, we call passively connected, because we're not intervening in the system. People are deciding by their own free will, and they just do sampling and collect. But now, the output, this is the input. The output that we like to do, like a couple engineers here, we would like to answer questions, or the query is about the effect of actions or doing. What would happen had we done something in the system? Then, most of the answers are about the causal effects. That is about policies, if you're a government, treatment, if you're a hospital, decisions, if you're just an agent and you want to decide. Then that's the tension. The research here is about the fundamental methodological question is about how to use the data collected from observations, that is layer 1, to answer questions about interventions, that is layer 2. Because those are different worlds. What gives us the license to do that? Yes.
I would have said there's as much data from layer 2 as layer 1. We just don't know how to identify it. Because every one of those data points from 1 came from something that caused it to be that data.
Yeah, good point. Let me paraphrase that. Layer 1, the decisions are being made. People are making the decisions in the world and decide, do I go to this drug or do I take this medicine or this other medicine? Do I enroll in the university or in higher education or don't enroll in higher education? do I get this language training or don't language? In other words, agents are deciding in layer 1, 2. The difference between layer 1 and layer 2 that we don't know the causes because we're not in the mind of the agent in layer 1. Then we don't know what is driving them to act in the way that they are acting. That's
The data's there, we just haven't figured out how to collect it.
yes, yeah, we're kidding, but this is the task. The task here, the formal version of the task is like, can you massage the data from layer 1 and do something with this in a way that we can extract the information that is as if you have done the intervention there. That's the task. And it's a class, it's a beautiful problem. But this is why, in addition to being well defined, there is the practical problem about how to answer queries for each of these layers. Yes.
Is this similar to offline reinforcement learning where you want to take observations or just collect?
Very related.
But now you want to do offline causal? That's actually just similar to
Yes. In the RL, what we'll say is like, RL can be longer. The RL is like, I have offline data and I'd like to make a statement as if I am online. Because online I'm doing the experiment. Now, we can zoom in there. I will defer. There's the whole world to do with. Yes. Let me just ask about the logistics. What is our logistics here? Are we going to do return? Okay, I'll get some questions, but I'll try to move a little bit to let me get here.
I understand that it's not impossible, Professor, but isn't it very difficult to go from just data where, like, okay, people did things or machines did things, even if you have millions or billions of data points, to go back from that and figure out why those choices were made?
Very hard. Yeah, but is it the two parts here? Part 1, very hard. Part 2, inevitable, because we need to understand, doing this translation from the amount of data and the correlation to have understanding of the system. This is what we need to do.
So it's very hard, but not impossible.
Yes.
Okay.
And inevitable. We need to, the hard or not hard needs to be done. I wouldn't focus on the hard. Nothing that we're trying to do in general is easy. Maybe fun, maybe meaningful, but easy is hard to get this one. Let me move slightly faster here, but I appreciate the questions. I think the idea was to have the conversation, right? Let me see what I want to do here. Let me move a little bit then around here. Now, I'll continue with this one. I'm a slide panel, maybe I have 40 or 50, and I don't think that we'll see how much I can do. But it's okay. Maybe I can share the slides if you are interested. But I would say, you have this world, and then you have the result that I said so far, just in kind of picture here, is about there exists a causal model or an observed nature, reality that can be modeled by a causal model, that's called M star. The only result that I said so far that this model induces this causal hierarchy, or the PCH, the pro-causal hierarchy, sometimes called the ladder of causation. And the ladder of causation is constituted of encompasses qualitatively different types of interactions of the humans with the subjacent reality. One type of interaction is related to observations, the red one. Another type, there is one probability distribution for the observations. Another type of interaction is related to actions, interventions. And we just talked about the tension between red and yellow in the previous slide. And there is the third one that is the layer 3 that was related to the counterfunctions. This is the potential of the system. In practice, we don't observe. This is just a cartoon, but you don't observe, let's say, yellow and green. We just observe observation, the passive data. Now, let's say that you would like to train an AI model. An ML model, I have a neural net that is the best technique in this decade at least. That's called the MHAT that we usually use in stats. I also teach stats, I think it's important. It's a kind of mix of computer science and stats. Then you have the MHAT, and you like to train that. Now, MHAT, if you kind of analyze, it does have the potential of inducing the PCH. It's just a data structure, and it could generate some observational distribution, it could generate some interventional and counterfactual distributions. But now, what we are currently doing in our TAC, this is the potential, layer 1, layer 2, layer 3. Now, what we're able to mimic what's going on with the truth that is the one in the left. Now, our question here is about what about this part of the data structure that is related to the effect of intervention? What if I had taken the drug? Would it be alive? Then I call this the fundamental problem, which says that under what conditions inferences in the m-hat side, in the right-hand side, are valid. In other words, when do they recover this inference procedure, learning procedure in reality? When do they recover the distributions induced by the 2m star that is shown in the left? And in principle, there are so many degrees of freedom in this type of model here that you can fit anything. Then it is non-trivial to guarantee, quote-unquote guarantee, even a probabilistic calibration sense that someone asked, but in a probabilistic sense, broadly, that this guy would be even closer to the yellow on the other side that you cannot see, and the same with the green. And that's the fundamental problem. At the moment, this is the cartoon of the illustration of what we are doing nowadays. Quite naive. We're being quite naive. Yes.
Are these neural models, like things like diffusion models or generative adversarial networks? So they're generative neural networks. Okay.
But in principle, could be because this is the current best for doing many of things. But it could be anything. You can even show formally that could be anything. That means if this one was exactly the same, just to show the challenge for even if you have data that you have an AI agent that is both observing the world, that is the red one, but the agent also have our authorization, quote unquote, or we are granting them the possibility of interacting and acting in the world, that is the yellow, then we have a more kind of another constraint there in the learning, subject to another constraint in the learning system, and we are able, let's say that it takes some time and you are able to learn, and if can replicate the yellow, we don't have a clue about what's happening in terms of counterfactuals and the wide type of questions or this deeper level of understanding. Now, our goal, we are in the beginning of the talk, but our goal here is to develop the next generation of AI systems that are endowed with the following capabilities once we understand the basics. We would like them to have some level of causal understanding of the system and the capability of articulating explanations, explaining why they are doing the things in the way that they are doing. We would like them to be more efficient. That's efficient here, I mean sample efficient. Not 10 million data points to do something very clunky, but be sample efficient and also be more surgical in terms of the intervention. If they have, multiple degrees of freedom for intervening, at the moment they are required to intervene everywhere. And this is not how we like to operate. We like to be soft, we like to be surgical. Even if I can intervene in 10 things in the world, I would like to be parsimonious, right? To just go in the one guy there, move this variable, right, wiggle here, to bring about the change. I don't want to change the whole thing. People don't like intervention so much. It's quite intrusive in some way. Then we would like to be more precise. Without understanding is impossible. We just have this quote-unquote, is a technical term, a fat hand intervention. You're putting the hand in there, being the whole mass, the whole splash there. Governments are very good at doing that. But we like them to be more generalizable and robust. Also like to have this causal and counterfactual type of generations. And we like the model to be able to do some kind of learning and discovery. Right? Because the model, the M star that I'm saying, is contingent in whatever age or experiences that the model have. You like it as us, right? As we are. And as it progresses in life, you start kind of creating new variables and new understandings and upgrading the model in some way. Our causal model, they should be doing the same. At the moment, it's quite static. Now, I like to give examples of some of them. I'll not go over all of them. Let me see. Let me give the one called causal explanation. The book is, again, as I said before, each part of the book is one of these kind of, I consider these the challenges or the tasks. Then let me just give an example here. US Census data, more mundane here. US Census data 2018. This, by the way, there's a few hours lecture there in this fairness.causal AI. I'll talk here in 30 seconds or 1 minute. There's a few hours of discussion about this slide and the elaboration of the explanation and fairness. let's say that we're trying to analyze the effect of gender on salary, and maybe gender affects, because we've seen that we got the data, we do some cleaning, spend a few, sometimes weeks after cleaning up the data, and then we get the TV, or total variation, right, the TV. We use here, apologies for the jargon. The expected value of Y, the average salary, given that is male minus the average salary from the female, I think it's $14,000 difference. Now, and we would like to try to explain why the salaries are different. Because the difference is not, the difference is life. The difference is good many times. But the question is like, what are the reasons for the difference? What may be explaining that? For example, gender, there are different mechanisms about how variations in gender may be affecting salary. For example, one option is that it's directly. There's this direct link. Gender is directly affecting salary, meaning maybe the HR person is, I don't know, biased in some way. The person comes in, they say male or female, and I'm just saying for the other genders, but for simplicity here, male or female, person comes in, they'll say, I'll put the salary down here because I don't like this gender. Then this is the meaning of this link here. It's a direct discrimination. They call disparate treatment in the law. Okay, this is one mechanism that could be explaining these disparities in the salary. Another one could be disorder. Maybe gender is affecting education level, and education in turn is affecting salary. It's a classic in reality, in high tech at least. Maybe gender in computer science, if we're talking about next generation of AI engineers and scientists, we have underrepresentation of female students. There are many causes, but not my analysis here. This is factual. Now, if the company should decide the salary, they are giving a bump, 100K more for someone that has a PhD. In other words, they are looking at education level, PhD, yes or no, bump the salary 100K. Now, without looking at gender, automatically they are giving, the ladies will be getting lower salaries. Then, and maybe okay, depending on the law, depending on the context. It's called, by the law, this is called business necessity. That the company, the Google or high-tech company can say, man, I'll go bankrupt if I'm not allowed to see what is the education level and compensate accordingly, I'm going out of business. Then the law will say, the judge or the jury will say, it's okay, that is even this figure in the law, saying business necessity. But still, you are generating the disparity in the data. When you check, when you go to the context, you expect a better salary given gender, you will have the disparity there. Then this is one mechanism. Indirectly, through, for example, education. Or the type of job employment here. It's called mediator, by the way, because it's mediating the relationship between gender and salary. Gender affects this thing, there's W, and W downstream affects the Y. Now, the third possibility here is like there is other things that are correlated with gender. Maybe the nationality. Nationality is correlated. I don't know what, not that gender is causing the nationality or nationality is causing gender. When you go to the data, you can see that maybe you have a overrepresentation of some group. Maybe there's some immigrants from Mexico, I guess. Possible. It's possible. I don't try to causally explain, but the correlation is there. Now, maybe the employer is using the nationality, not the gender, as the input. Then, again, these will be translated in some kind of disparity in the value of the average salary. Then, after legal argument, the jury may be okay with maybe kosher that Y variations that are due to education. Then this is okay, kosher, it's okay. You can look into education. But it is not okay variations that are due to gender directly, or the gender that is covariant with age, and age cannot be used. This is not good. Now, our question here, methodological, data layer 1 is just saying that. So the disparity is there. The question now, how to disentangle the variations that are in TV and attribute them to each of these different mechanisms. Or explain in some way. This is just a little plot. Those are two, not the parts here, but this is the total variation. I think the difference, at least in this data set, with the census 2018, to federal employees, the 14K was the difference. And this is this disparity here, 14. This is one type of explanation. This is the direct one, it's called the direct effect. The other is the indirect effect that is through the data, through the education and employment. And the other is what we call spurious, that is the one through age and nationality. Now, one explanation is that all this disparity that you find in the data is explained by the ones that are coming from the spurious ones. This is one possible explanation, and this is a completely different explanation, that the disparity is going mostly directly. The guy there, the HR or whoever is doing the compensation, is looking into gender and changing the probabilities of going higher or low, which is totally not okay, in general at least. Anyhow, this is just one to ground an example. TV, total variation, again, layer 1 cannot distinguish causally different explanation. It's compatible, equally compatible, which is not what we want. Anyhow, I would be happy to take a look if you are interested in fairness.causal AI. There's a few hours tutorial there, and there's even some lectures. Or drop me a line if you want. I spent a few weeks even in class trying to do the theory behind how to produce explanations of this kind, and this is just a cartoon example, one data analysis. You can do all over the place, whatever X, Y, and Z variables you have. I will not do this one, but college admission, you could do explanation as well. You can kind of try to track, this is another that is in the paper, you can kind of try to track how much bias we are in our decision making. There's affirmative action, we need to balance this and that, and so on. This is, I don't know, from 2010 to 20, this is kind of the direct discrimination very related to affirmative action, that we're kind of changing the probability depending on some type of group, demographics, and this is the other kinds of bias. I will not open up, but this is in the paper, kind of interesting as well, when you have time series type of data, and you can kind of track that. Now, I would like to,
Just a simplistic question. What does this bring to the table that classical multivariate analysis, multivariate statistical analysis, doesn't bring?
no, they will not, you will see more in the TV, in general, in the general aggregated measure, and if you try to do some type of decomposition like that, very hard to get, and very hard meaning is not the most common, but there is some subparts of the literature that they do it in general is very parametric or very specific. I don't know, we have linear, Gaussian, we have one very special case here where can be any kind of, can be non-parametric, included any kind of model, and so on. I want to mention just, this is another one, I will skip the details here about the reinforcement learning that someone asked. It's an important one. The example that you have is, I will not read it here for the sake of time, but it's about some type of leukemia trials, completely different domain of the economics and the health sciences. The link here, sorry to have to point to the link and not be able to talk fully here. This is the causal RL, the reinforcement learning, the CRL.causal AI. This is a trial related to leukemia and neuroleukemia and placebo. Let me just move to the picture here, please. And maybe this is a two-stage trial. The person comes, and then you wait a few months, and they come for the second shot. This is the X2. And then the X1 and X2 are the treatment. Choose lots. It could be whatever number you want. We need to define it. It's a technicality here. And then you have the state. Whatever state was the patient, we use that to make the decision about the trial. The U here, that is an important guy, is the unobserved confounders. In other words, you have in the wild, in the hospital, there is this unobserved variable that physicians, for whatever reasons, they are deciding to give the treatment. There is some that is maybe also affecting the state of the patients. And this is the outcome Y. You're trying to optimize Y, that is the survival of the patients, for example. Now, then you use state 1 as an input to the decision 1, the first shot. And then this will affect the state of the patient later, that we'll kind of measure, and this should be the input to the second shot. Now, the kind of classic randomized trial multi-stage. The interesting part, I will ignore the lab for now, the interesting one is about if you go the route, kind of more FDA route or randomization. I forgot to read the title. Usually even discount points for the students if they don't do that. X-axis is the number of interactions, kind of the number of people that are kind of coming, the number of rounds. sounds that we're getting these people. In the literature is called episodes. And the y-axis is called the regret. Regret here is a technical one. We can just do that in theory, but the regret means if there is an oracle that knows what is the right thing to do, minus what we are doing. Because we're not the oracle, the system or the physician, we make mistakes. Now it's some kind of measure of mistakes. We call regret in the literature. And this is the cumulative regret. If you go FDE route and do a randomization, that's what we got. And in reality, after even 10,000 kind of patients that we do, we still didn't learn. We still don't know what's the right treatment, what's the right treatment. Things will get some kind of log like that. We need to maybe to go to 100,000, then this curve will be something like that. At the moment, we got still kind of blown out. We don't like that. We're linear in this way. We like to have some kind of super linear. Now, if you use, the interesting part is like if you use just a more clever randomization, you kind of can already get this type of behavior. In other words, this means that the AI was able to learn. They know how to assign the treatment and learn the protocol in slot time 1 and time 2. And here is the most interesting, because the problem becomes trivial in reality. That is the green line here. There's no almost learning needed. Just with the data that you have from layer 1, that is observational, with bias, we can kind of massage that in a clever way. Use a little bit in the very beginning. We could zoom here. There is a little bit of attempts here that we're flipping coins. You are flipping the coins in a biased way, and you already learn very fast how to give the treatment. And I think it's a cool one, useful to the medical setting or any kind of decision making. Or just getting the medical because it's a classic area in the literature. There's a lot of discussion about this particular trial, but it's a methodological type of advance. Now let me move. I don't want to go over that one. It's in the CRL.causal.ai. I would like just to mention now my last task here, the causal generative capabilities, what I mean by that. Because I even got some questions about what is generative. I'm not sure if you're familiar, but we have this MNIS that is related to the digits that usually started very popular in AI in the 90s that for the US Postal Office. We don't want the person to be looking the zip code there. I think it was around the 90s, early 90s or so on. You would like some kind of AI to read the zip code and do the redirecting. Not a task that you like to do. Now, you kind of have the breakthrough there at that point. But anyhow, just for actual history here that we're talking about false credit card fraud, some of this conversation is going on for a long time. But now what's peculiar about this particular data set that is the enlarged version of the MNIS, this is called the color MNIS. And the color MNIS is special in the way that you have the digit from 0 to 9, and then we also have a color. And the color is correlated with the digit. Right? And the correlation is shown in this dash. This is a graphical representation here, in the dash bidirected arrow. Now, maybe if you have a 0, there is a probability distribution here that zeros tend to be very rare. On the other, in these data generating model. On the other hand, the 5s are very cyan, kind of bluish. Cyan is the color in the US. Now, and then there is some kind of sampling. You get some kind of randomized number here, and these affects the color of the digit, the color and the digit. And then you go and take the picture, and then you get the image I. This is by 32, anyhow, the dimension of the picture. And then the figure. And then this is what we get. We get these little patches like that for each. Then you see that we got zeros that they are pretty much a very kind of rat-ish. The probability distribution, not all of them are like that. But it is concentrated around the rat. Now, I would like to go through the layers. Let's say that we like to do generation, to be generative, and I would like to sample from distribution. I want the images given that the digit is equal to 0. And this is something called the GAN, if you're generative adversarial network, if you've heard, or the diffusion models that is a very popular word in the last year, the top one in terms of performance and so on. They are doing exactly that. They are trying to generate realistic images from the data. This was the data. We input that, the system learned, and now I say now I just like to sample zeros. That is naturally occurring zeros. But now, what about if I go to layer 2 and I'm like, no, I don't want the naturally occurring zeros. I would like with my own actions here in intervention, I would like to sample from the distribution P of I given do digit B is equal to 0. Then we would like to force the digit to be 0. Then we're kind of cutting this correlation here between the digit and the caller. Because we are the one doing the intervention. This is not happening in nature. Which means that we start getting zeros from all callers. Because we're kind of averaging over this caller variable here. And this is an example of an intervention. Layer 2. Picture way of doing it. What about layer 3? This is just a cartoon just to get a feeling about what's an intervention. This one is a counterfactual, layer 3. The digit was naturally a 5. But you ask, I would like to sample from the distribution what would be the image had the digit being a 0. It was a 5, the same as the drug. The guy took the drug, I wonder who would be alive not taking the drug. The digit was a 5, just like a color scheme of that. What would happen had it been a 0? And now this is what we get. We usually don't have zeros that are cyan. Those zeros tend to be red. But now, given that it was a 5, it means that it is in the DNA, quote unquote, of the digit. The color cyan, this correlation here. Then you start getting kind of more cyan-like zeros. And this is a counterfactual. The M is just a classic in computer vision. Let me just show my last example. It's a little bit more realistic. I hope you like the image because I think it's very cartoon cool. But this is more real now. You're very used to say also get that name. I'm in the computer vision domain here just to show visually some of the stuff. Then maybe you have a Rossky and you ask AI, please turn the Rossky into a wolf. And then you get it. And then it works well in reality. A lot of the running here of the companies nowadays is about scale. How do we make higher quality images in the right side? Not the game that we're playing here. The game is the following, or the question is the following. What about if you have multiple concepts and there is some level of correlation across this concept? Maybe two concepts here in the human faces, let's say, is about there is age, and age is correlated with gender. Maybe it's true, by the way, in the data science classic, we have more males that are older and females that are younger in the classic data set of faces. Now there is a correlation there. It's not balanced. It's never balanced, by the way. It's a very strong correlation. Now, someone could ask the AI, make a person look older. It's possible if you're not using, this is the picture original one, you get not a older, but you get a guy on the other side. Which is kind of totally off, right? It's not what we'd expect. Now, why is this happening? Hard to take. But in reality, because the correlation is overwhelming the system. Because of, anyhow, if you use causality, we're able to get give me a picture of human face, and get this one and say, how it will look like if you give 10 years of age to the person, and you get the other one. Makes sense. Another example, the same data set. Maybe you have smiling. Smiling affects whether the person is their mouth open or not. There is a positive effect. If you say smile, it's more positive that you'll be opening your mouth. Now, and then you can have the smile, the opening mouth, and then you take the picture and you get the face, the human face. Okay. Now there is an inverse. If you say what would happen had the person been with the open mouth, this shouldn't affect the smiling status of the person. The person may be in a bad mood, just with an open mouth. It's a different thing. But now this is what we get. The non-causal one, if you say, please give me a picture of a human face, you get these ones here in the left. But now we're saying the non-causal, say, what about had the person been with the open mouth? Someone may be appearing that is more smiling than they are in reality. You're not preserving this type of invariance. While if you do the causal, the guy may be okay, and here's just open mouth. If the guy is smiling, of course he should be smiling with the open mouth. Again, just cartoon to convey the idea that there are causal relationships, even in the human faces. And if you want to do generation, we would like to preserve these relationships. Example that I showed before. Maybe there is female or male. This is just a label in the data set. Like F means female or male. This is correlated with young or old. That is Y. But age, that is Y, is a fact whether the person can have gray hair or not. And there is this direct effect. There is a causal effect from age to the hairline, let's say. Now, and you have all these attributes, and then you take the picture, and then you have the image here. Now, making a young person look older should lead to more gray hair due to this effect, but it shouldn't change the gender, of course. And then this is a kind of thing, so the non-causal one, this is the original pictures that were generated by AI, and you see what would happen had it been older, and sometimes you get a male on the other side. And this is the causal, usually it is consistent with basic knowledge. It is cute, but we're starting to use some systems like, not necessarily this one, but downstream for many tasks and automate stuff. You have crazy results if you cannot provide this level of guarantees. These are just an example from another paper. They are getting the input as the farmers from 100 years, and you say, make them look like doctors, and then you kind of change the gender.
Because it was non-causal.
Non-causal. And people are very surprised. They're, what's happening? We are surprised in some way, but it's not, in some way, if you zoom in, it's not surprising, because it is totally overwhelmed just by the correlation.
Because the training set had a lot more male doctors than female doctors.
That's right. This was from a few hundred years, and it's the data from this type of, it's even more, yes. But the important point here is this is just a cute picture. The point is about methodological. How do you take this type of knowledge, causal knowledge, into account in order to produce guarantees for this generative method? Let me keep moving here. The conclusions or comments, I would say, causal conclusions very strong. Causal inference and AI are fundamentally intertwined, and novel learning opportunities emerge when this connection is fully understood. This is an important one. Most impediments for general AI or more general types of AI today are orthogonal to the current acausal methods available in machine learning, including deep learning and reinforcement learning. In practice, failure to acknowledge distinct features of causality almost always lead to poor decision making and superficial type of explanations. What's the goal here? The research program is to develop a general framework, and what I mean by that is a set of principal algorithms and tools for designing causally sensible AI system, capable of integrating these three modalities: observational, layer one, interventional, and counterfactual data, modes of reasoning, and knowledge. And this will lead to a natural treatment of human-like explainability and hopefully more rational types of explanation. Thank you, and also thanks to the lab. This is an effort for many, many people. The guys in the lab is from my lab, the guys in the right